Dobro večer svima i dobrodošli još jednom u Astronomski centar Rijeka. Na večerašnjem predavanju okupili smo se, prvo predavanje u ožujku koje je posvećeno Suncu. I s obzirom da će predavanje biti na engleskom jeziku, onda ću odmah ja isto se prebaciti sad na engleski. And I want to wish welcome to our lecture for this evening, that is Giorgio Rizzarelli, who will be speaking about the sun and the solar activity in this 2024, which will have the solar maximum. And Giorgio is our colleague and collaborator and friend from the Center for the Astronomical Studies in Trieste. He was studying theoretical physics at University of Trieste, but he's also been working a lot in the last 10 or 15, 20 years, observing the sun and the activity of the sun. This year, the sun, as we said earlier, will have the maximum of its activity. Possible. And today, Giorgio will present us some measurements and some photos also that he made in the last few months, and he will explain in details about the sun behavior in general, but particularly with the emphasis on the solar activity in the last few months. Also, before we start this presentation, I would like to mention that both Giorgio and Andrea will join us in the expedition of solar eclipse, which will occur in 1 month, in April, in Texas. So we are really glad that we have both of them tonight, this evening, and also after presentation lecture we will have the final arrangements for this expedition. And now I would like to invite our lecturer Giorgio Rizzarelli. So please, Giorgio, come here. The floor is yours, and enjoy. And for all of you, I wish you to enjoy this lecture. Giorgio, the floor is yours.
Thank you. So, dobar večer, dobrodošli. This is where my Croatian ends. my grandmother was from Dalmatia. I was a very lazy boy. She wanted to teach me Croatian, but I didn't want. Now I regret. So, solar maximum, we don't know really, there are prediction. The sun activity is not regular in time, it has some variability. The main component of variability is that every around 11 years it has a maximum in activity. So there can be made some predictions, and also according to the latest observations of the last months, the sun is very active, so it is quite likely that the solar maximum will happen this year, maybe next year, but anyway, it means that this will be an interesting year for observing events like, for example, this. The energy of 1 billion Hiroshima bombs, nuclear bombs, is released in such an event. This is called a solar flare. It is basically a flash of light, not only visible light, but also higher frequency, which are more energetic. For example, extreme ultraviolet, which is what we see in this image. And this happened on New Year's Eve. It's a nice coincidence, but we started the year with fireworks, and it gives a good indication that it will be an interesting year. And we had also various other events intense in January and February, and this was the most intense event since 7 years, since 2017, which was in the previous solar cycle. There is nothing to worry about. I mean, these are extreme energetic events there on the sun. They have some effects on Earth, because of course a part of this energy reaches also our planet, but we are mostly protected because the atmosphere of Earth has layers which filters extreme ultraviolet, for example. We also have a magnetic field which shields us from other kind of solar phenomena about which we will talk about. So when there are some effects of solar phenomena on Earth, they usually are only in the high atmosphere. For example, aurora borealis. And there are also some problems with satellites, and only very rarely, there are some effects also here on the surface. So, January and February already had not only that event, but many others. This is kind of a bit of technical history, but well, flares are events like the one you just saw, flash of light. When you see an X, X means that it's the most intense class. So these are more significant events. And as you see, we have already many of them. This is not unusual. It is usual for a year of solar maximum or for a year near the year of solar maximum. And in addition, we had big sunspots. In particular, at the end of February, we had the biggest sunspot so far of this 11-year solar cycle. We will see the briefly photos. And also, another interesting event is we had a strong eruption. We will see later the photo of the polar vortex on the southern pole of the sun. Okay. As I said, one of the effects, terrestrial effects of the strong solar events is aurora borealis. During a year of solar maximum, it is more common to have intense solar phenomenon, and as a consequence, also the aurora borealis can be more intense, and it can get down to low latitudes, not only polar latitudes, let's say mid latitudes, like here. This photo was taken in Slovenia. And actually there were 4 or 5 times last year in which the aurora borealis were seen and photographed in Slovenia. So this is one of the nice things about a year of high solar activity. So solar cycles, you see the activity of the sun in the latest about 30 years. Really, it's about 2 centuries that astronomers watch the sun, and so we are arrived at the 25 recorded cycle. This is the third cycle, and here are some predictions. The green is the observed data, and the blue and the red curve are predictions. The blue curve is the last prediction, the old, until around a few years ago, 1 year ago. Then came a group of researchers which did a prediction with a new methodology, which predicted that the solar maximum will arrive quite earlier than previously expected. That is not in 2025 or 6, but in 2024. Of course, these are predictions, so they have their uncertainty, so we are still not sure it will be late 2024 or early 2025. But you see, the data is quite in agreement with the prediction. Other things you can see from this graph is that the previous cycle, 24, 10 years ago, was not so strong. And it seems from the graph that the present one is stronger. And another interesting thing is that the latest cycle, the 24, was double peaked. That is, instead of having a single year with maximum, we had 2 years of high activity, 2012 and 14. And this is interesting because possibly it's due to the fact that the 2 sun hemispheres are not perfectly synchronized. So every sun hemisphere has its own cycle of activity around 11 years, but if the 2 are slightly more off synchronization, so we have a year of maximum for one hemisphere and a year of maximum for the other one. We still don't know if the present cycle will have a single peak or 2 peaks. My personal opinion is that it will be single peaked because the activity is growing faster and stronger than previously expected. So probably it will be faster and intense, just one peak with more intensity, but also because there has been an event, at least one event, really one, more than one, which involved simultaneously the two hemispheres, north and south. There has been a sympathetic flare, which means that we observed simultaneously a flare in two different points of the sun, east and west of each other, in two different hemispheres. Okay, so how do we, oh, by the way, what do we use in this graph to measure on the vertical axis to measure the sun activity is usually the number of sunspots. This may seem strange because sunspots are dark, cold zones, they seem boring, but it is exactly from sunspots that usually the energetic events like solar flares and eruptions of some material come. So this is a good way to measure the sun activity. So this means that during a year of solar maximum we have many sunspots, and during a solar minimum we have a blank sun, more or less. And also the sunspots are used since 2 centuries to echo solar activity because they are relatively easy to observe. They don't need much technology. As a matter of fact, the first sunspots were observed in history around 1000 after Christ, how do you say in English? Okay. By Chinese astronomers using no technology, by completely naked eye. And this is a thing that you can do also today. In fact, if you have a big sunspot, like the one we had in late February, it has such dimension of the disk of the sun that you just need the resolution of the human eye without needing any magnification. And if you have a sunset with much mist and regular clouds, it can act as a natural solar filter, that is, it dims the light in such a way that the sun is not anymore so blinding. So for a few seconds you can stare to the sun and you can see, well, there is not much contrast in this projector, but you should see that here. I did this photo in this way because to render what I did so with the naked eye, and I can assure that it's quite an experience because when you see a thing without the aid of instruments, you really believe it. Okay, but usually you don't have these special conditions, so another thing you can do, still if you have a big sunspot, is using a pair of these, be sure you know, eclipse glasses, even if you don't have an eclipse. And this is what you would see, a blank, a blank disc with a white disc with a black dot. This, if you use a particular brand which produces a particular material called ASTRONOMSKI, which guarantees that you are seeing the color faithfully of the sun. So, if you watch the sun in a midday, in a full high in the sky, you will see that its real color is white and not yellow, as we imagine. Yellow is a product of the Earth atmosphere which modifies the color. You will see a lot of pictures yellow, but they are artificially colorized because in your imagination the sun is yellow. But the real color is white, and this is very important because it gives us some information on what really is the surface, the sun. I mean, what we are watching in this way is the same thing which we see naked eye blinding, that is the last layer, dense layer, before it becomes transparent to light. And this is called the photosphere because it emits most of the light of the sun. And its real color is white, which, as you know, I have put here a very scientific image of the spectrum. So Pink Floyd family recognized it. And it's the same kind of light which comes from an incandescent light bulb, And so we know for sure this means that the photosphere of the sun is an incandescent body of a certain temperature, which is about 5,500 degrees. Okay, so if you want to have higher resolution, or if you don't have such a big sunspot, you need magnification. Here you have to be careful. Of course, probably you know you should never point any magnifying optics to the sun without protection, because it's very dangerous. And in the focus, you will focus the bright light of the sun even more bright at the point that it will burn everything you put in the focus, which is the eye of the photo camera. So you need a protection, which is basically using the same kind of filter which is in the eclipse glasses, for example ASTROSOLAR, but you need a larger filter because you have to put on the objective side. So it's not at all safe to watch into a telescope the sun using this. You have to put the filter on the objective of the instrument before the light enters, before the light is concentrated, in such a way that all the aperture of the instrument is covered. And well, you can buy this material, not to do promotion, but because how many of you have a reflex or mirrorless camera with a tripod and with a telelens? Okay. You can do solar astronomy with a few tens of euros, because you just need to buy this. This is a sheet of this material, and you just construct by yourself something like this, a filter to put on the objective. What you will see many sunspots, and so you can begin already to do some solar astronomy. So the two basically features that you see in the white light on the photosphere are, of course, the sunspots, but also on most of the surface you have this texture, which is called granulations. These basically are bubbles. The sun, which is boiling, because of we say the photosphere is an incandescent body. So you can imagine it like an ocean planet, but instead of water, it's a kind of a lava, a white lava. And about the sunspot, where you see it's usually formed by two zones. So there is a dark zone inside, or one which is called umbra, and then there is an intermediate zone. Umbra, there are many details, but we don't have time to discuss them. And here is instead the granulation, which I just spotted, the bubbles. This is, by the way, an animation. These are very high resolution photos, which are done with a 1 meter diameter telescope, which is in Palma. And you see that this is quite valid. Each of these granules has a duration of about 10 minutes, so this is a time lapse. Okay, so next, what do you notice about sunspots? Where the first thing you notice that they go from left to right. This is because the sun has a rotation around its axis. This is the same thing which happens to Earth, but in the case of the sun, the period of rotation is around 1 month. Not exactly, because it has a differential rotation. That means that on the equator it turns faster, a little bit faster than on the poles. And other things you can notice is that this should in theory go forward forever, but in PowerPoint it doesn't work. Okay. And other things you notice is that you can see, for example, which is a group of sun, which is rising from one border or setting from the other one, being born, dissolving, sunspot with joint, which split, change shape, move, rotate. So even if you have telelens with a filter, you can have some enjoyment for some months with the sun. But the most important thing to note about them is that they are like people. They don't want to stay alone. They want company. They are mostly in pairs or in groups, but they prefer to stay in pairs. Of opposite sex, well, because there is a deep reason about that. Here you see two, so a pair, two pairs of pairs, another pair, another pair. And the deep reason about this is the reality about what sunspots really are. They are magnetic poles. They are very intense magnetic poles. So you know, on Earth you have just the North and the South Pole on the roughly on the geographic poles, but on the Sun, in general, this is not the situation. You have many magnetic poles in different points of the Sun. And this you can see with your eyes using these kind of pictures which NASA can do of the photosphere, but more refined with a particular technique which is called magnetogram, which shows the magnetic field of the Sun, which is colored here in green, yellow for the two polarities, green, blue for one, and yellow, red for the other. And here I have put two examples. The first one is a quite a regular, simple sunspot, a pair of two opposite polarities. As I said, I like to say two. And here there is a more complicated one, the giant spot, sunspot, which we just saw, which was present to the Sun in February. And let's look first at this one. Of course, if we look at the magnetogram, we see that it's not only the two sunspots that are interesting, but the entire zone which is between them and also around them. Because if we think in three dimensions, we notice that we have a magnetic field which goes from one pole to the other, and so the entire zones inside and around are interesting. Which also means that if we are able to watch a higher elevation above the photosphere in the thin air above, we can see interesting things, as we see shortly. This other example is a complex sunspot like the one we had in February. You see it has a multitude of magnetic poles intermixed together. This means that I don't even draw the magnetic field. It will be very intricate, twisted, complicated. What happens with a sunspot like this is that it wants to make some cleanup. So at a certain point, which is usually in a few days, if you have a sunspot like this, you can predict that it will eliminate one or more of this extra pair of magnetic poles to make some order, to get closer to a more simple situation. And this, of course, will destroy all the magnetic field which is between two pairs. And this contains a lot of magnetic energy because, of course, these are very intense magnetic fields, and also the scales are big because this is the air, just to give it an idea. So, when this happens, the Sun, that sunspot, liberates, frees some energy in a violent way, which is usually in one or both or two ways. One is the flare, which we saw in the first slide, which is energy in the form of light, and the other is energy in the form of movement, that is an eruption of some material which is similar to the eruptions of volcano. Okay, so we need to watch in higher elevation, and the most simple thing without technology which we can do is watching the total solar eclipse. And with the moon covering the photosphere, so it doesn't blind you, you can see the layers above, and the first thin layer you notice is called the chromosphere because it's red. This can be actually seen by naked eye during a total solar eclipse. As pink because it's very bright, so it's saturating. The real color is a deep red. And then there is the corona, which is a higher elevation. elevation layer, still thin. And what's very different from the photosphere, which we saw before, of the chromosphere, is that it is very thin. So it's kind of like a gas, not a lava. So it is not an incandescent body, but it glows light with a very different mechanism, which is similar to gas lamps, for example neon lamps, or street lamps. The old yellow street lamps are sodium lamps. They glow yellow because it's the color of sodium. The sun is mostly composed by hydrogen, so it glows of the color of hydrogen, which is called hydrogen alpha because it's the strongest color which emits, and it is a deep red. If you don't, by the way, you see that the chromosphere is not a regular layer, but has the so-called prominences. So there are pieces of the chromosphere which gets a trip, like clouds on Earth, on a higher elevation in the corona. Okay, so if you don't have a total solar eclipse, you must use a filter for this red color. This is a very specific wavelength, so it's an expensive filter, so this is a kind of astronomy that an amateur can do, but a little bit more expensive, but it gives you more satisfaction because it shows you, as you see, much more features. For who is interested, I brought here some instruments. These are all H-alpha telescopes, and we start from kind of 1,000 euros, just to give you an idea, for the most simple instruments for observation, and we get to a little bit more, that kind of 2,000 for instruments which are suitable for photography. I don't have time to speak about the equipment, but if anyone is interested, this is a bit more specific, we can talk about the questions. I will show you some features which we can see in chromosphere. So basically the durable features which we see are two. One is again the sunspots, but not only the sunspots, but the entire region which contains the magnetic field, which is called an active region. And here are also active regions. And the other feature, which instead you don't see in photosphere, is the prominences. And this particular prominence is in two pieces. The piece which is against the disk is seen in backlight, so it's dark. It's called a filament, and this other part is called a prominence, but it's really the same thing. It's just two names from the same. And these are the two main features you can see: active regions and prominence. And there are also two kind of violent event explosions you can see with this technique. One is the flare, so you don't see it much spectacular, it's aesthetic, but you can see it. That is an emission of light. And the other one is the eruption, that is an emission of some material. Okay, then there is the general texture, which is not granulation. So on photosphere you have granulation and sun boiling, but this is kind of elevation, you have kind of many hairs. The sun is hairy. These are these are called spicules. It's like grass. Many little prominences which last about 10 minutes, then disappear, but completely continuously reappear. And so they form a texture on the entire surface of the chromosphere, which is influenced by the magnetic field, so it's not completely the same in the surface. Okay, so I now give you some example of these features. The first, the active region. This is the same which we did see before, the giant sunspot of February, seen in white light and in chromosphere. In chromosphere. Do you have some water?
Yes, I can.
I'm sorry. In chromosphere, you see that it is more interesting because you have much more detail. And okay, this is instead an active region, so the first one is player, which is this one. And this is an eruption, instead of some material. And this is a combination of two, because flares and eruptions usually happen simultaneously, not often. So you can have sometimes one or the other. These instead are examples of prominences. Prominences are of many different kinds, kind of 30. I just put 3 to 4 to make an example. Some of these images are done by myself with one of those solar telescopes, and which is the first two, particularly the second one is a time lapse. Sorry. Yeah, now it's going. So it's a time lapse. So this is done by one image every minute, and it covers around 1 hour time. So you see that with this technique you can see the sun evolving. And instead the one here is taken from scientific high temperature telescope, and it is much more detailed. Okay, also filaments can have their violent events, can erupt. This is very clear from the image on the left, where you see an explosion of a filament. The one on right here is one particularly spectacular. This happened in 2012, which was in the latest, so maximum, about 1 years ago. And this one happened recently, is an eruption of the south polar vortex, which I told you before. These are things which happen only on the solar axis. This is a marvelous image taken by the 1 meter telescope in La Palma, which shows you simultaneously the regular texture of the photosphere and of the chromosphere. So you see the granules, that is the bubbles of the symbol in the photosphere, white light, and you see the speakers, the kites of the sun, which are kind of transparent, so you see it's like more thin air. Okay, and the last layer, which one can look more external, is the corona. To watch a corona, you can use a total solar eclipse, but usually this is more difficult for amateurs because corona is very hot. This is a strange thing. The fact that when you go up into space, the temperature intuitively should go down, instead it's quite hot. To give you an idea, we have millions of degrees in the core of the sun, where we have nuclear reactions, then we have thousands of degrees on the photosphere, and then we have on the corona millions of degrees again. This is one of the unsolved problems for astrophysicists of the sun. We still don't know why that. But it means that the corona emits light in quite higher energies, so quite higher frequencies. And so to watch it, you must use, as I told you before, extreme ultraviolet. And extreme ultraviolet don't reach the surface of here, the Earth, ground, luckily. So you must use something in the space to watch it. And luckily, NASA has a satellite, a geosynchronous satellite, which is right above the atmosphere, and it's called Solar Dynamic Observatory, which has quite lots of filters to watch these lines in extreme ultraviolet, so to watch the corona in a spectacular way. These are just two of the wavelengths of extreme ultraviolet which you can watch. And on left, I have put an example which shows you the main feature. The corona is basically formed by loops, which are similar to prominences, just like they are more regular in form of arch, and like here, and they are quite higher, quite bigger. You can see very good the face on corona, and there are also these structures which are called coronal oils, from which sometimes some material flows out. The one I put on right is an event which happened in January, which I quoted before, is a very rare kind of event called a sympathetic flare. That means we have two simultaneous flares in two very distant points of the Sun, which is not a coincidence. It has been shown that this kind of event, they are connected one to each other, and they are, as you see, in two different hemispheres of the Sun. So this kind of an indication that, as I said before, maybe the two hemispheres of the solar cycle are synchronized for the maximum. Okay, so do you have any questions? I see very bored faces. Do you have any? Is it okay? Do you follow me?
Yes.
Are you sleeping?
Yes.
Yes, okay. Now, let's speak a little bit more about the solar cycle. So, probably you could have some questions. So, first question, what is this cycle? Where does it come from? Why does it last 11 years? Why do sunspots, which are dark zones, are also zones of very intense magnetic field where there is this connection? So, I will try to make clear these questions, and to understand this we must get inside the structure of the Sun. So, as Pink Floyd says, certain controls for the current Sun. And well, very briefly, I will quote that there is the core where there are nuclear reactions, nuclear fusion, with most of all of the energy of the Sun is produced. I cannot get into detail about this because we don't have time. The following layers are for transferring energy or heat to the exterior. And there are two. One is called the radiative zone. In this layer it's the light which travels, the heat. And the second, which is more important for us, which you see will be the origin of all solar cycle or the solar phenomena, is called the convective zone. The convective zone is very similar to this, the classic pot of boiling water. And you have a separation, of course, because of the temperature, so you have material, it's lighter, so it goes up, and then it gets colder, and it's down. So when we are watching the photosphere, which is simply the top of the convection zone, we are watching the top of this convection cells, so bubbles, just like in this example. Then we have the other external layers, which we called before, the chromosphere and the corona. An important thing about the convective zone is that it is fluid. That is, this is where some material moves, while in the radiative zone is kind of like a solid, it doesn't move. So in convection zone you have mainly two kinds of movements. One is the convection, which is toward the exterior, so then we have circulation, and the other kind of movement is the rotation of the Sun. So this is the layer where the Sun rotates. In radiative zones, down there it goes not. Okay, so what is made the Sun of? It is made mostly by hydrogen, then there are other elements, but the important thing is that it is in a state of matter which is called plasma, which is similar to gas. Gas is where you have thermal movements and the particles are free one from each other. Plasma is even hotter, that the pieces of the atoms are free one from each other. And the important thing is that the pieces, which are electrons for example, are electrically charged. So this plasma is an electric gas. Since there is a thing which is called electromagnetism, which says that electricity is connected to magnetism, it also means that plasma is an electric but also magnetic fluid. So when you have plasma, you always have magnetic fluid. So in fact, in electromagnetism, if probably you know, if you take a coil of electric current, attached a battery, you have constructed a magnet. This is called electromagnet. So current generates a magnetic field. And so in the sun, the current, well, the sun rotates and it is made of plasma which is charged. The sun material, the plasma, generates magnetic field. And conversely, magnetic fields acts on currents, so acts on plasma. So there is a kind of mutual influence between the matter of the sun, which is the plasma, and its magnetic field. And this is the main notion to understand how the solar cycle comes out. At solar minimum, the magnetic field of the sun is very simple. It's like the one of the Earth. We have a very similar situation. We have just two magnetic poles on the north geographical, the south geographical, and magnetism is very weak. It's comparable to the one of Earth. So if a compass, you go on sun, you can use it, but only solar. Sorry? And when, as the sun rotates, remember that the sun has a differential rotation, so on equator it moves slightly faster, it drags with it the magnetic field lines. So you see that the piece of the lines which are around the equator goes forward and they form these loops, these U-shaped forms. Month after month of rotation, and then year after year, it's dragging the lines, and you arrive at this very complex situation where you have these U-shaped forms, which of course are inside the convective zones, because there is the fluid in the convective zone, there is where the magnetic field is formed, but with the convection, it goes to the exterior of the sun. So there are some pieces of these U-shaped forms which get outside the photosphere, so pinch it in one point and another point, one point enter and one point exit. So you get the picture which I showed before, that you get, this is basically a prominence because it is a line of magnetic fields, a flux, tube flux of magnetic field lines, but it can contain some material, so this is how prominence is born, and it is also how a couple of sunspots is born, because these are extra magnetic poles. So you have at solar maximum a completely different situation with respect to solar minimum. You have a magnetic field which is not at all the poles, but it is basically at lower latitudes around the equator. It is very intense, is chaotic, is unstable, is completely continuously changing. To give an idea, the intensity of magnetism here is kind of like 1,000 more than the poles on the solar minimum. Okay, and still missing piece is why are these extra magnetic poles, that is the sunspot, why they are black? Why do they appear as such? So we just have to remember that magnetic field, conversely, acts on electric plasma, and so what it does is disturbing the movement, the normal movement of the plasma, which is the convection. So disturbing the convection is kind of like this magnetic monster turns down the fire under the boiling hot water. So this zone of the sun, instead of hot, becomes cold, and as a consequence it also becomes dark. And so the magnetic field lines exit with this configuration, and you can see the traces in these lines on the previous switch. Okay, so returning to, this is kind of completing the picture of the previous slide from solar minimum to solar maximum, and then we get to solar minimum again. So you can imagine that you initially have a simple magnetic field north-south, then you gradually in 5 years get to a complex magnetic field around the equator, and then continuing you get again to a poloidal magnetic field, so another solar minimum, but the two poles have exchanged role. So after 11 years, the situation is not the initial one, but you have completely turned upside down the entire magnetic field of the Sun. And by the way, this actually happens also on Earth, but luckily in very long epochs, like 500,000 years, otherwise it would be catastrophic. Okay, so this is what really is the solar cycle. It is an oscillation between two very different states of magnetic field, poloidal, equatorial. Equatorial very intense. And well, we can actually observe that. This is a nice montage which an amateur has drawn about the current cycle since the minimum to the latest year. And you can see there are much more sunspots now that we are close to maximum, but not only, we have also many sunspots which are close to the equator at lower latitudes. You can also plot a graph. This is the graph of the solar cycle, and this is called a kind of butterfly diagram because of the form, and it shows you something which is a little bit of surprising. That is, the solar cycle isn't time symmetrical. I mean, the second half of the solar cycle, which means in your case from this year, next year to 2030, will be much more interesting than this first part, because as you see from the graph, the sunspots are less in number, but are still near the equator. Then, when you arrive at the end of the cycle, which is here, you have a discontinuity. So there is a moment when it is an end of cycle, which will be for the cycle around 2030, where the Sun still will have a good number of sunspots around lower latitudes, around the equator, and then suddenly, in a very short period of time, it will do a general cleanup. So that is a very interesting period, which is called the termination. It has been studied in very recent times, and it is very short. I mean, it's kind of like less than one solar rotation, so 2 weeks. And respect 11 years of solar cycle, that means a very precise moment in time. And it is exactly using this notion that that group of researchers have done a more precise prediction recently about this solar maximum. Because if we know with a good time resolution when was the last solar minimum, where the cycle at the beginning, which was at December 2019, January 2020, you can do a very precise prediction with a resolution of, let's say, 1 month of the next solar maximum of this universe. Okay, this is an alternative theory about the origin, just one slide, an alternative theory about the origin of the solar cycle, which I personally found much simpler. Well, you remember the cells of convection of the boiling water. In the pot of boiling water, really you have a supercell, which is a pot, but you have also little cells inside, which are the bubbles. And it's similar in the Sun. You have little bubbles, which are the granules, then you have bigger structure. And this recent theory is that you have 2 supercells of convection, so 2 big pots, boiling waters, which are simply one hemisphere, the other hemisphere. So, according to this theory, what simply happens is that during the cycle, the Sun has this kind of circulation. This very simply explains how you start from magnetism on the North Pole, and then you gradually get it transferred to the equator. And it also quite simply explains how the 2 hemispheres can have kind of independent cycles activity, so they may be kind of slight auto-synchronization, and so we can have a double peak solar cycle. Oh, by the way, physicists have done a calculation of which is the duration of this circulation of material, and they have found 11 years, so it's a good model for the solar cycle. Okay, do you follow me? It was a bit difficult, this physics. Okay. Something more to get into at the end, something more entertaining. Aurora Borealis. How does it work? How can we predict? How can we follow the news to prepare ourselves for the bats to go in a dark sky to see aurora? So this is basically what happens. You have an eruption of some material on the sun, which usually happens when you have a solar flare, which means, if you remember, that you need to have a complex sunspot with a very intricate magnetic field. If you have the flare arrives, it's light, so it arrives just in 8 minutes. It arrives now, soon, on Earth, so you have kind of a warning, because the eruption of some material, the bubble of plasma, travels in slower, because it's matter, in 2 days typically, 2 to 5 days, but typically there are 2 days. So if you have the news that you have a strong flare with an associated eruption, which is called technically a coronal mass ejection, this mass the sun ejected from the corona and gets in space, and if it is now in the direction of Earth, of course, you know that 2 days after, probably you will have an aurora. So you have all your time to prepare your bags, to call friends, to organize an exit in a dark sky, moonless, away from city lights, just for the conventional space. You follow the news for prediction for aurora. When it arrives, what happens is this. Mostly we are shielded from plasma coming from the sun, because we have a magnetic field, which is called the magnetosphere, so the material flows out. But there are these 2 channels where it can enter. It's not really the material enters, but what really happens is that the plasma takes with it magnetic field, so interacts with the magnetic field of the Earth. It's kind of like urto, come si dice urto in inglese? Shock, impact. And this impact transfers energy from this bubble of sun plasma to the magnetosphere. So you have a disturbance of the magnetic field of Earth, and this is called a geomagnetic storm. A disturbance of magnetic field in electromagnetism means generating an electrical current. So this is kind of like a battery, or a dynamo, if you prefer. There are also some electrical wires, which are some lines which goes to the pole, of course, to the north and south poles usually. And you have a lamp. So basically what happens is that there is electricity coming from the sun, which lightens up the high atmosphere of the Earth, which is composed of various elements, but what glows more easily is oxygen, which glows usually on green and sometimes also on red. So this is, very simply speaking, what is aurora borealis. So there is a nice analogy with the sun here, because we have seen also that the chromosphere of the sun is kind of a gas lamp that is red, and that is kind of perennial eternal aurora. We have sometimes, and usually just on the poles, on high latitudes. But as I said before, if we have an enog intense event, which is common at solar maximum, we can have also a big geomagnetic storm. There is a scale about that, technical scale, which goes from 1 to 5. For all latitude, we need a G3 to see something, a 3 level. If you get a 5, go out to see, because it's spectacular. Here are some examples. There have been no less than 4 or 5 times in last year, in 2023, that aurora borealis was seen here, near here in Slovenia. And these are the photos. They are all taken by the same amateur, which is called the hour cuts. And these instead, these were G3 and G4 intensity. And this instead is a G5. These pictures are taken in Italy. This is Cortina d'Ampezzo in the Dolomite Mountains. And this is taken in Slovenia. This was 2003, was a year of solar maximum, was a strong solar maximum, but we still don't know, but it is possible that the present solar maximum will be kind of near to this one. So this kind of level, G5, happens kind of 1, 2, 3 times for each solar cycle. So you have to take the occasion, take the chance when it happens, because you need also to have moonless nights, to organize your cycle free, to have good weather also. And well, finally, speaking about the prediction of aurora, I will give you very shortly in 2 slides some suggestions about websites if you wanted to follow some activity, because of course not many people have the passions of the desire to use a kit method to watch by yourself. Oh, by the way, in your club, one of those solar scopes are property of the club here. So if you come here in the day, take an appointment with them, you can watch the sun. And of course it's quite more interesting watching by you. But if you wanted to watch the news about the solar maximum using the internet, there are many web resources, but here is my personal selection, just 2 websites. The first one is called Space Weather. I use this thing every day, because every day it gives you the most important element. So the digest, not many, but just the most important things. This is a typical page, every day it changes. You have on left the daily picture of the sun in white light, so with the sunspots. Here is a few rows, the notice if there is some interesting sunspot which may track or you see its glass index of flares. This was when this is of today, I think. No, this was from a few months ago. And on the main page, you see the news. So, for example, here a flare happened, you have the photo of the flare, and here is also written that an eruption accompanied the flare, and there is also the prediction for the geomagnetic storm. Here you see G2. So, if you read here G3 or more, that means probably you will be able to see aurora in these latitudes if you have good weather. And well, the other website I can suggest is the official website of that space observatory, which I quoted before, Solar Dynamic Observatory, which gets a lot of pictures in all possible colors, photosphere, chromosphere, and also corona. And you get daily pictures and also historical pictures, so if you want to check the particular date. And so, good luck for seeing the aurora.
Good luck, and thank you, Giorgio, for this presentation tonight. And now, as it's usual, after a presentation, we have some time dedicated to questions and answer session. So please, now it's your turn from the audience.
You answered the first one, so I did. Okay.
Okay. Okay.
The photos for Slovenia all coming from Maribor or up there north? Or?
No, the first one I showed was from Maribor. The other ones were from the same amateur, Javor Katza, which is from Dolenia Vas, but I really don't know which Dolenia Vas because there are many Dolenia Vases. But I will write to you. I will write to you because I'm curious. Because honestly, I never succeeded in seeing the aurora. it's not so easy really in practice, because you have to have, as I said, a ready. I was free, I was informed, but it was completely cloudy, overcast. And that guy in Maribor had a piece of clear sky in the right moment. It's not really so easy in practice, also because geomagnetic storms have their durations, which can be from 2 to 8 hours. So if it's only 2 hours, but at all latitudes where it is weaker, it is even less, like 50 minutes, you have to be lucky to be there in the right moment. So if you are an amateur astronomer which is there to photographing the sky, the galaxies, for example, for all the night, it's good for you because you have time to lose. Okay, you are there all the night. If you are going to watch the aurora, maybe use go with a G4 or G5 when you are more sure that you will get a more intense and durable experience. Bene, coraggio, dai.
Next question?
I have a question about the rotation of the core of the sun. Because you spoke about the core and the radiative zone, which are rather solid.
Yeah.
I would like to know how is the rotation of that part of the sun.
As far as you know, they don't rotate.
Okay.
So there is a zone which is the interface between the radiative and the convection zone,
Yes.
which is called the tachocline, and that is a very interesting zone because it's where in a relatively short distance you pass from having no rotation to have the rotation. And according to the latest research about about the predictions from the solar cycle. The tachocline is here.
Between the zone 2 and zone 3.
Yeah, exactly. That very interesting moment of the solar cycle, still not much studied, which is the end, the southern end of the solar cycle, which happens in 2 weeks, when it does the final cleanup. So you have many interesting events in compressed in just 2 weeks. Seems to be connected with this zone, with the tachocline. Seems to have origin there. So this is interesting that many things which happen on the surface and the surrounding of the sun really have their origin quite in the deep interior.
Another question?
The scale of the flares, does it also go up to 5, x5, or does
Yeah.
That's the highest?
The size in practice?
The highest is x5.
No. Okay. The X is the letter for the highest class. There are 4 letters. B, C, M, X. Every letter is a power of 10. Okay. And everyone goes from 1 to 9, 0 to 9, but X goes from upper numbers. And the largest recorded with an instrument is X45. That was the aurora in Cortina. The aurora of 2003, Cortina and Slovenia. Remember, it is not really the flare which makes the aurora, but it is the plasma, the coronal mass ejection of plasma, which is usually simultaneously happening with the flare. It's not always the size of the flare which matters, because sometimes you can even have no flare. because, for example, you can have, like in 2012, there was that filament eruption, which I talked before. This happened from a zone, there is also a flare here, but it's not the same zone. This happened in a zone where there was no sunspots. Usually in this case you have no flare, so it is useless to use the number, and still this film can be very effective on Earth. This eruption was so intense that it was the same intensity of one which happened in 1959, which was the most intense solar storm recorded in history. We didn't have an instrument in that time to measure the class of a flare, if there was, but we know of the effects. That is called the Carrington event, was very much effective. It caused aurora borealis at very low latitudes, intense, but overall these induced currents was so strong that they damaged the telegraph system, the telegraph grid. They also caused some fires on the telegraph grid and also some shocks, electric shocks to people working. If that kind of event happens today, it will be much worse, because today we are very much dependent on electric grids. Think about the internet, mobile phone, the power grids, and also the satellites, which are in high atmosphere, so they are quite... that event was caused by an eruption like this, so even without flare, it can be a disaster. But they said yes. We don't know Carrington. Carrington probably had a flare also, and it was very intense. We don't know the scale because we don't, probably more than X45. Yeah. The largest recorded is 45 in 2000.
You thought that we are safe from
Sorry,
the...
but I think Sven raised the hand a bit earlier, so...
Are we doing that? No problem. Did you have a question?
I want to ask about solar storm, but never mind.
Sorry?
I want to ask about the solar storm, but never mind. The silly answer.
You want to ask about solar storm?
Storm.
Yeah?
But you already answered it.
You already
answered.
Ah, okay, okay.
You thought that we are safe on the Earth because of magnetic field and
Yeah.
atmosphere, but what with ISS astronaut up?
That's different. Well, speaking about when you use the word solar storms, that is not a scientific expression. It's a little bit vague. Really, there are three different kind of violent events. For now, I just quoted two because I didn't want to put too much information. The flare and the eruption of some material. But there is a free kind which is a little bit similar to eruption. It is called a solar radiation storm, so that is more properly as a solar storm. Or better to call it solar proton event. That means that you still have some ejection of material from the sun, but it is protons, which are heavy particles, so they are very penetrating. In this case, it is not like aurora borealis when it is a chain of indirect events. It is directly the particles, heavy particles from pieces of the sun, protons, or heavier nuclei, so, that come directly on people. Okay? We are mostly shielded by the various, but in more higher you go in elevation, more risk you have. So, if there is a solar proton event, we had two moderate ones in January and February. The people which are flying in aircraft at high elevation in polar routes, which is common because for geodetic they do, can be exposed. Usually not to kill them, but it's like getting a TAC, you know, tomography, okay, many radiographies. Well, it is more worrying for a pilot because he flies every day, okay, so it's more likely that he gets some exposition. If you are an astronaut, of course, the thing is more serious. This is the reason why people in the International Space Station stay for a maximum of 6 months. This is one of the reasons. And well, still, International Space Station is here, is inside the Earth magnetic field, but can you imagine being on trip to the moon? If I'm right, this year Artemis will take people.
Not with people, I think.
Postponed.
Not still?
Still not with people, yes.
Okay, so in a few years
Lecture in
people
June.
will go again. When just when you are outside of the influence of the Earth, you are on the trip of the moon, you are more exposed, and if you are on the moon, you are even more exposed. So making bases on the moon is not trivial. You have to be under meters of rock to be. So even being in a spacecraft it's not easy to do a project for a mission on Mars because in the spacecraft you have to have a zone to have more protection, to shield the people, but it will not give total protection because you cannot do meters of material in the spacecraft, so it's not easy. And on Mars it's even worse. So maybe some of you we remember that about 10 years ago there was a private entrepreneur which was the one which he developed with the Big Brother copyrighted TV show, and he wanted to do a project, completely private project, to take people on the moon, on the Mars, sorry, directly colonizing it and sponsorizing the entire project by a TV show. And well, it was completely nonsense because we still have to solve some problems like this one. And, so you don't go to take a walk on Mars so easily. Just a few minutes per day. Then, you have get your radiation.
There was a contest, right, among 100 people, and then they, the private entrepreneur.
I actually met also one of the boys which was part of the 100 selected.
Yes.
He did also a conference, he was very convincing, but...
I think also there was one Croatian guy from Šibenik who got in the top 100, but then the project just seemed to have stopped at some point. It was in 2014, something like that.
Yeah, probably some of them did know, so they knew, because they also got money from this thing.
Okay, we still have time for some questions.
If no one has questions, I do one question. This is possible. Because it's a thing which I find very fascinating and interesting. What about other stars? Okay. You may think that what you have learned today for the Sun is learning also about the other stars. Many things are similar. So you have nuclear reaction, for example, in the core. But many other things are different. This is quite interesting. Like people, we are different, also the stars are different. If we limit ourselves to the stars like the Sun, which are, I mean, in the mid time of their life, adult, not old age, there are the stars are classified according to color, that is the temperature of the photosphere. And two extreme examples in addition to the Sun are this was for the questions. If you have questions to me, I prefer already the size. Two extreme examples where the red are the red dwarf, so it's a red star, red because it's cold and quite small, and a blue star like Vega, which has been quite studied in the latest years because it's quite near. Like this. And well, red dwarf first. what's interesting, it has no radiative zones. So different structure. Most of it matter is convection zone, percentually speaking. So this means that it has a high activity. So these red dwarfs have powerful flares, much more than the sun, which can double light few times, or very giant sunspots, because they are big like the sunspot on the sun, but the star is small, so the sunspot covers half the surface of the galaxy. So if you have a planet around a red dwarf, and it has been discovered, of course, it is not much likely that you have evolving life, because the star is too much unaffordable, dangerous. Conversely, Vega, or a blue star in general, is much more interesting. First of all, you see its oval, because it rotates so fast that it, for centrifugal forces, shape. And well, according to the theory, until a few years ago, it should have the radiative and the convective zone inverted in order to respect the sun. Just to give you an example that. And that means that according to the old theory, the surface of Vega should be no convective zone, so should be smooth. No magnetic field, no sunspots. And instead, in 2015, a researcher has discovered that Vega has some magnetic field on the surface, and it also has star spots because of star spots. But even more interesting, as you see from this is of course a film art picture, these star spots are white and not black like the sun. But also on the sun really they are white, because according to a recent theory, what really is a sunspot, we are seeing the tip of the iceberg. We are seeing a red zone on the surface of the sun, but it is very high in the deepness of the sun, of the convection zone. And at the base, it's white, it's hotter than the surrounding. And in the mid part, it's circulating like a tornado, as a cyclone. So we have this analogy with why does Vega displace this kind of structure? We don't know. Physicists don't know. Possibly it has a second convective zone in the exterior, or maybe has completely different mechanism which we don't know.
We're approaching little by little to the end, so maybe time for last question. Maybe last two questions if there will be quick questions. Before we finish, I have one question. So the stars are usually distributed according to color, so it's usually spectral distribution. And we have different colors: O star, B stars, A star. So the sun is classified as G2 star. It means that it's a yellow dwarf star.
Yellow-white dwarf.
Yellow-white dwarf. And why do we call yellow stars? Is it do they really exist, or it's just they're similar to our sun and we call it yellow because in our atmosphere we perceive it as a yellow color when it's high above the horizon?
I don't know, possibly it's a historical thing about that. Yeah.
It's a historical thing. So
remember, it's a G2, so it's
G2, yes.
Toward F.
Toward F.
Yeah, possibly it's a historical thing. About classifying a structure, I think that mainly there are these frequencies. So what we learned about the sun is about all the G, F, and also K, which is orange stars. Speak loudly, please.
Yeah, what is the class of a yellow hypergiant?
I don't know about them. I mean, they are old stars, giant or hypergiant, etc. Are stars which are close to the end of their life.
But yeah, like I was talking about like stars like Rho Cassiopeia, that's like a yellow hypergiant.
Yeah.
So what is that, like an intermediate phase between the blue hypergiant and the red hypergiant?
Possibly Loro knows more about me.
There are obviously, in order to reach that phase, it has to pass some in-between steps from, from the giant in order to reach the hypergiant phase. There are a lot of branches in Hertzsprung-Russell diagram, and according to the initial mass, some stars can pass through some phases, evolutionary phases, which are not so common and usual for stars which are of the lesser mass, for example, as it is for our sun. So it depends on the mostly depends on the initial mass and various different chemical compounds and so on. So the story is not very straightforward and simple. So, but yeah, there are some evolutionary phases, even some evolutionary phases of stars which cannot be achieved by only single stars. They have also to be in some binary systems in order to achieve some special phases which are not, which cannot be obtained in just single stars systems such as the solar sun, for example.
Thank you.
Even maybe it will be the very last question.
Actually, the sun spots are bright, but due to brighter surroundings, it's like optical illusion. So we see very, like, I don't know, very dark spots, but actually they are bright.
Sorry, are you speaking about the sun? Or?
Yeah, the sun spot.
Yeah, can you repeat?
As I understand, around the spots are more brighter surroundings.
Ah, yeah.
neighborhood. And the sun,
yes,
this
yes.
is optical illusions that they are so dark.
Let's take a picture. Yeah. Okay, on one, let's take a high resolution picture because I know about the amateur photos, but sometimes, well, you here don't see that. I don't exaggerate with the aberration, so probably it's a kind of optical illusion, but say in photographical sense that someone puts too much contrast. But let's check, because I'm not sure, a professional photo with a kind of 1 meter telescope. I try one here. No, but there are bright zones on the surface, not in the direct surrounding of the sunspot, but inside a group of sunspots. I didn't mention that feature because I want to keep things simple, but you can see them here. They are called facole on the photosphere. Okay. You usually see them on the border because you are watching in transparency, that's so to speak, but they are everywhere. There are other filters which shows you on the photosphere structure, and also on chromosphere you see something similar. You see in the surrounding of a group of sunspots, you see frequently this kind of structure, which is similar to a flare, but more stable and not so much round. This has been called plage, which is a French word which means beach, because they are kind of distributed.
Beach.
Yeah, plaza. But for historical reasons, correct. But this is very interesting because it is debated of what these really are. But probably the fact is this. I told you that when you have a very unstable sunspot like the one giant which we have in February, very complicated, it unleashes energy in violent way. But what about all the other ones? Or the same for the rest of the energy? They dissolve gradually. Where do all this energy go? This is another of the unsolved problems of the solar astrophysics. Well, maybe the answer is trying to answer simultaneously to this and the corona heating problem. So, you, according to a theory, you have continuously in an active region microflares, many microflares continuously. So, it seems it is not violent, okay, but there are many little emission of light, and according to this theory, all these things, the faculae on the photosphere, the plages here, there are also a thing which is called Enderman bombs, which are little points, white points, which you sometimes see. All this discharge gradually the most of the energy of the magnetism of the sunspot. And where do this energy goes? It is not a violent release which goes toward the Earth, for example, to make aurora. They go probably into the corona. So this is probably what explains why the corona is so much hot.
Yeah, probably the color, the dark spots are not that black as usually appear. They are probably a temperature of 3,000 to 4,000 Kelvin, which are reddish in color. But I think the question about optical illusion, yes, when it's compared to the rest of the surface, it appears like a dark spot, especially in some filters, in some bands. They look like they're completely black, like here. But usually, if you take a closer look, it would be like orange or red kind of.
Apart of the fact that the picture on the app is artificially colorized in Photoshop, okay, so it should be white. But it's right, I didn't want to complicate things, but it's right. If you have an incandescent body, which is colder, and well, the internal part, the so-called umbra, is 2000 degrees, the external part, the penumbra, is around 4000, and this is around 6000. So this is like a piece of red dwarf on the sun. And this is like a piece of orange dwarf, kind of pieces of other kind of stars on the sun. Well, according to the physics about the light emitted from the incandescent body, not only the intensity of light is much different, but also the color. So, of course, you know, 2000 degrees means red. So, really, the core of the sunspot is red. But we don't see that because not only is red, but it also is much less intense in light, much darker than the photosphere. Because the law about the intensity of the light from the incandescent body is that you have the 4th power of the temperature. So it is 1/3 of the photosphere, 2000 is 1/3 of 6000. It means you have 1 on 80 around of the intensity of light. So typically the photo camera don't have much dynamic range, and also the eye. So if you watch visually or photographically the photosphere, in practice you see them as black. But really they are red. They should be red.
Okay, I think this will be now right time to conclude this, at least official part of our gathering this evening. So if you have more questions for our lecture this evening, for Giorgio, you can feel free to ask him later, maybe in Galileo Bar, just over there. And I will use the opportunity to thank once again to our evening guest, to our Giorgio. And before we start this unofficial part, I would just like to invite you for the next week's event that we will have here. So it will be the first AstroPop quiz of this year, and this time we'll change a little bit of the format. So the quiz will not be just one single event. It will be the first of the 4 quizzes that we will organize this year, which will count as a league. So the final prizes will be awarded at the end of the year, and the last appointment, the last pop quiz in this series we will have around Christmas time. So this time you will have like a special league, so you can compete for not only just one time, but you can also collect points from 4 different editions of this year's quiz, which will also be dedicated to our 50th anniversary of Academic Astronomical Society, which we celebrate this year. Okay, thank you very much once again, and hope to see you next time on the pop quiz. Thank you and good night.